In this video, we'll be discussing a few basic parameters of optical communication. One of the most important characteristic of an optical fiber is its numerical aperture. It is the measure of light capturing ability of a fiber. Another very useful measure of a fiber is V number. It summarizes all the important characteristics of a fiber in a single number. Before going into these topics, we'll discuss another important fact. There is a cone of acceptance at the end face of a fiber. Rays arriving within the cone can propagate through the fiber, and the ones arriving outside this cannot propagate. This cone is known as acceptance cone. Let's have a detailed picture of this.
This diagram represents an optical fiber. The inner layer is the core, and covering the core there is a cladding space. Optical pulses travel through this fiber using the principle total internal reflection. The light from an optical source will be focused onto this fiber. First, we will consider the case an optical pulse is entering. I am terming this as ray 1. This line represents the normal. The incoming ray has to undergo a refraction here because the refractive index of the core and that of the outside environment is different. So the ray will deviate from its original path. Here, reaching this point, the light beam has to undergo another refraction because it is the core cladding boundary. As this is a fiber, total internal reflection will occur. This action will be repeated until it reaches the other end of the fiber. By focusing the light beams in somewhat greater angles also, the signal was found to be propagated smoothly through the fiber. We will now consider another ray with a greater angle. To propagate light inside a fiber, it must strike the core cladding boundary at the critical incident angle or above it in order to provide total internal reflection of this light. Satisfying this condition, the ray could reach the other end. The transmission of signals through fiber was possible up to this angle. Beyond this angle, the conditions for total internal reflection could not be met. Let's see what happens with a ray which hits the boundary with a greater angle. This ray hits the core cladding interface at an angle less than critical angle. Thus, total internal reflection will not be possible. It gets refracted into the cladding and it will be eventually lost by radiation. It is evident that all lights that are lodged into an optical fiber will not be propagated through the fiber. Only rays with a sufficient angle at the core cladding interface will be transmitted by total internal reflection. In this case, we can say that rays lodged up to this point could be propagated through this fiber. Thus, we can say that for rays to be transmitted by total internal reflection within the fiber core, they must be incident onto the fiber within an accepted level. Considering the three-dimensional effect, we can say that there is a cone of acceptance and we can term it as acceptance cone. It can be defined by the conical half angle theta A. Theta A is the acceptance angle. It is the maximum angle to the axis at which the light may enter the fiber in order to be propagated. Now we will discuss another important term, numerical aperture. This parameter is a measure of the ability of the fiber to gather light at the input side. Thus, it can be represented in terms of acceptance angle. It is defined as numerical aperture is equal to sine of acceptance angle. Numerical aperture can be expressed in other terms also. We will try to derive some other relations for numerical aperture. The optical fiber is represented here, and as said earlier, this will be the cone of acceptance of this fiber which is defined by this acceptance angle. Here it is termed as theta 0. The refractive index at this portion is defined as n0. Here we are considering the light beam is traveling in air. So the refractive index n0 at this portion will be 1. The refractive index of the core is indicated as n1 and refractive index of cladding as n2. Here the numerical aperture can be expressed as Na is equal to sine theta 0. Deriving other expressions for numerical aperture, we will first recollect the Snell's law. It can be generalized as n1 sin theta 1 is equal to n2 sin theta 2. It can be explained as the product of the refractive index of the first medium and sine of the incident angle, and that can be equated to the product of the refractive index of the second medium and sine of angle of refraction. As the first step, we'll consider the refraction occurring at the core cladding interface. Theta 2 is the incident angle at this position. According to Snell's law, it can be written as n1 sin theta 2 is equal to n2 sin theta 2. We know the basic requirement for total internal reflection. The angle of incidence should be greater than or equal to critical angle. So we'll start from the basic criterion. The angle of incidence is here considered to be as critical angle. We know when a beam is incident at critical angle, then the beam will be refracted at 90 degree. So the refracted beam theta 2 can be replaced as 90. Sin 90 is equal to 1. So we'll write it as n1 sin theta 1 is equal to n2. Now we can write sin theta 2 is equal to n2 by n1. We can mark this as equation number 1. Now we'll consider a right angle formed here. Sin theta 2 can be measured as opposite side by hypotenuse, and cos theta 1 can be adjacent side by hypotenuse. By calculation, we can see that cos theta 1 and sin theta 2 are equal. From equation 1, we can write cos theta 1 as n2 by n1. We'll mark this as second equation. Now we'll consider another trigonometric rule. Sin x is equal to root of 1 minus cos square x. In that format, we can write sin theta 1 as root of 1 minus cos square theta 1. By equation number 2, we can write n2 by n1 instead of cos theta 1. Sin theta 1 is equal to root of 1 minus n2 square by n1 square. Now we'll apply Snell's law at air-core interface. We can write the first section as n0 sin theta 0 is equal to, at the core side, n1 sin theta 1. We know for air, n0 is equal to 1. So we can rewrite the equation as sin theta 0 is equal to n1 sin theta 1. And from the third equation, we can substitute the value for sin theta 1. Now the equation will be sin theta 0 is equal to n1 into root of 1 minus n2 square by n1 square. By simplifying, we'll get it as root of n1 square minus n2 square. The expression that we get here is for sin theta 0. We started with the relation numerical aperture is equal to sine of theta 0. So Na can be expressed in another way, root of n1 square minus n2 square, where n1 is the refractive index of the core and n2 is the refractive index of the cladding. Numerical aperture is a very important characteristic of an optical fiber. It is a good measure of the light guiding properties of the fiber. We can connect the value of the numerical aperture with the number of modes. The higher the Na, the more will be the modes. For a single mode fiber, the typical value of Na is 0.1, and for a multimode fiber, it is between 0.2 and 0.3. For a single mode fiber, if the Na value is higher, then the attenuation is also high. Similarly, with a multimode fiber, if the Na value is higher, then there will be a greater level of dispersion. Thus, numerical aperture is related to a number of fiber characteristics. Another important term related to an optical fiber is the V number. It is also known as normalized frequency or fiber parameter. This can be represented as V is equal to pi d by lambda root of n1 square minus n2 square. This term can be replaced as numerical aperture pi d by lambda into Na, where d is the core diameter, lambda is the operating wavelength, n1 and n2 are the refractive indices of the core and cladding respectively. The V number can be used directly to determine whether the fiber is single-moded or not. If the value is less than or equal to 2.405, then the fiber will be single-moded. And if it is greater, then it will be a multi-mode fiber. We can also calculate the number of possible modes. For a step index fiber, it can be calculated as V square by 2, and for a graded index fiber, it can be calculated as V square by 4. Thank you for watching.